My screen is visible to you, I hope. Is it? Okay. Is my screen visible to all of you? Like anyone of you can screen like white screen. Are you able to see white screen? Okay, okay, great. So when we talk about FEA, we generally talk about nodes, elements, shape functions. Okay. Now let us consider a simple case. Uh, so this is x-axis and this is y-axis. Okay, and I have a function y is equal to f of x that is equal to some constant, because that is constant, right? Y is equal to f of x. It is straight line or parallel line to the x-axis. That's why it is constant. Okay, and this is x1 and this is x2. Okay, so this is function f of x is equal to constant, some constant. Okay, now if I want to find the area under this curve, okay, under this curve, this is straight line, so this is area, this is that area. This area I want to find. So this is simple rectangle, right? It is simple rectangle with height as c and width as x2 minus x1, right? So we can simply calculate area is equal to height into width is equal to c into c is because that is value of constant. This is C, height x2 minus x1. So for this simple function, we can simply calculate the area. Now let us take a case. Let us take another case where we have some kind of this function. Okay, it is very much complex function, and now I have to find the area under this curve. under this curve I have to find the area, and area under this curve I have to find. And this function is very much complicated. Now, as for this is not like a square, not like a circle. This is not a regular geometry, right? So it is very much complicated. Now, by analytical methods or the exact method, I cannot find the area of this area under this curve. So now I can use approximate method. And how can I find it? Let us say what I am doing. Let us assume this area is made up of small areas. Okay, such small areas. Okay, small. Let us say this is delta x, or the, let us say if this is x1, this is x2, x3. Let's just say this is x4 and this is x5. So this is the width, and now here if we see this function, the part of the function, this, now this I can add all these small areas. Okay, let us say this area is a1, or this, if I say the total area is a, then I can add small areas ba1, ba2, ba3, all these small areas. Now to find this small strip area, let us draw this area, assume this area, this part only. In a zoomed way or exaggerated way. Now let us say this is the exact function. Okay, now I have this as x4 and x5. Okay, this width is same everywhere. Okay, but now the height is varying. Let us say this is h1 at this point, and at this point the height is h2. Okay, now I cannot use the formula of area, like area formula of rectangle. Rectangle का formula use नहीं कर सकते यहाँ पे, right? This is neither the rhombus, sorry, neither the trapezoid, neither the rhombus, because this function I don't know what is it. Okay, and it is not a simple function, or this is not a straight line as well. Now, what I can do, let us say first approach. In the first approach, I can assume that, let us say this is also h1. So I am neglecting this area. I am just calculating this area. Okay. So I am neglecting this area. And so now my area will be x5 minus x4. Simply like width. Okay. This is width. And this is the height into this h1. Okay. In first approach, what I am assuming, I am just calculating the area of rectangle, and this is my area error, because exact area is this much, right? And this area I am not taking into consideration. So this is my area error. Whatever the shaded region is there, that is my error. Okay. Now here we have higher error. Now let us say in second approach, what I do, I assume that Okay, let us say this is not the this rectangle, and let us say if I join a straight line from H1 to H2. Okay, I am joining a straight line from H1 to H2. Now I have little bit smaller error only. Error is reduced, right? Error in case of second approach, error in case of first approach. Now this is trapezoid, right? For the second approach, it becomes trapezoid. Okay. Here I have H1, here I have H2, and this width is x5 minus x4. Okay. And what is the area of trapezoid? Trapezoid area is like H1 plus H2 divide by 2 into this width. Width is x5 minus x4. Now the error is little bit reduced. Okay. Now in third approach, what we can do? I can assume the quadratic function instead of straight line function. Straight line, I can assume quadratic function here. Now the area will be again reduced. If I go to cubic function, the area will be again reduced. So as I go, let us say this is x to the power n. As I increase the polynomial degree, so error gets reduced. Okay. But it was like for a rectangle, it is like simple x to the power 0 because it is constant. For straight line, it is x to the power 1. For quadratic, it is x to the power 2. For cubic, it is x to the power 3. As we go on higher and higher, up to the higher and higher point in the error reduces. Okay, that is first thing. Now, how we can decrease the error? The first point is like we can change this function. And this function, whatever we are assuming here, that is called as shape function. Okay, shape function or the interpolation function. Now, what I can do to reduce the error as in the second way, I can decrease this width as well. If I decrease this width, let us say I reduce this width to very small width instead of this higher width. Now, this error will be reduced again. So first thing is by shape function. Okay. And second is, and this small areas or the small strips can be called as elements. Okay. The small strips or small areas can be called as elements. So if we decrease the element size, then also our error will. If we decrease the element size, we increase the order of shape function, the error will reduce. Now, what is the problem? So you will say that we should do it always, right? If you want to have the accurate solution, you should always have the higher order shape function or the higher order polynomial, and we should have always the proven lower element size, right? Smaller element size. But if we increase the, so if we decrease the element size to very in like infinitesimally, or if we increase the number of elements, then our computational power will be increased. We will require higher computational power. Let us say if we have 1 lakh elements, then we may require like 8 GB RAM. Okay. And let us say if we have increased the number of elements to 10 lakhs, in that case, we may require the our computer specifications higher, on the higher side. Let us say we may require 16 GB RAM. In the same way, if we consider linear order elements, linear order shape function, and if we let us say consider quadratic shape function, then our computational power will increase. So the limitation is from the perspective of computational power. If you have very good, and it is obvious that if you want to purchase, if you want to have higher order, high specification computers, or the have you want to have high computational power, you will require more money, right? So what we want to do, we want to optimize between the accuracy and the computational power. So we cannot go to low and low element size, and we cannot go to higher and higher order of safe function. So we have to optimize. Okay. So this is from the perspective of the element size and safe functions. Now we have seen, now wherever we want, we connect, let us say this is our simple raw element, and I have applied, let us say, force here F. Okay, it has area A, length L, and x modulus E. So this is simple rod, and I have applied force. Now I can assume it to be 1D element. Okay, and I am dividing this into, let us say, 1, 2, 3, 4, 5, 5 elements. Okay, I am dividing this over total rod into 5 different elements. Here it is node number 1, here it is node number 2, here it is node number 3, here it is 4, 5, 6. So, and elements are 1, 2, 3, 4, and 5. Now, wherever we connect these elements, that are called as nodes. Okay. And the smaller parts of the overall geometry are called as elements. Okay. Now, I can calculate, let us say if I want to calculate what is the displacement here, I can calculate displacement or what is the unknown at nodes. Okay, I can calculate displacement, say, strains at these nodes, and if I want to calculate these values in between these two nodes, then I need the shape function. So the role of the shape function is to calculate the values in between these two nodes. Okay. Now we have seen the nodes, limits. Now let us go to the boundary conditions. What are the boundary conditions? The boundary conditions are like whatever we know, that is called as boundary condition for the given problem. Let us say this is cantilever beam and I have applied minimally varying load W Newton per, let's say, mm. This is the length of the beam. Now, I know that it is fixed at the same, right? At x equal to 0, it is fixed. So, I can say that y or the deflection in the y direction will be 0 at the same. Also, I know that because it is fixed at this end, the slope at this end will be 0, right? So what I know these things, okay? So these are called as boundary conditions. I also know that at the rightmost corner, now if I draw the SFD of this cantilever beam, it will be like this, right? Here I have shear force equal to 0 at the rightmost corner, and here I have shear force is equal to W into L, right? W into L. This is shear force diagram. So at this x equal to L, I know that shear force is given as A into A dy cube upon dx, and that is equal to, we know that, 0 from this condition. Now the moment is also 0 at this point. EI d square y upon dx square, that is also 0. So these are called as boundary conditions. All these conditions are called as boundary condition, and all this we know. Now, with the help of boundary conditions, I can solve these differential equations to find the unknowns. And what are the unknowns? Unknowns will be y at any location, right? Slope at any location. This will be the unknowns, and I can find with the help of, by solving this equation, differential equation, I can put these conditions and I can find y at any location, dy by dx at any location. Okay, so that are the boundary conditions. So what are the types of boundary conditions? Okay, so let us see types of boundary conditions. So first, based on based on moment allowed. If you have any doubt at any time, you can ask. Does anyone have any doubt? Aniket, Faisal, Sagar,
No, sir. No, sir.
Vaibhav, Nilkant. Okay, these are the basic things. If you have any doubt, please ask me here itself, because these are the like, basic things. If you are not able to understand, if you want me to repeat anything, just please ask me. Okay, Faisal?
Sure, sir. Sure.
Yeah. Okay, based on the movement. So this I mean by movement. Let us say, okay, let me first list. Then based on the movement, we have homogeneous boundary conditions, homogeneous boundary conditions, and non-homogeneous boundary conditions. So these are the two types based on the movement. Now, what is mean by like movement? Let us say if I have cantilever beam or now I know that at this point at x equal to 0, some load
Sure.
F, yeah, at this point I have y is equal to 0, right? That is fixed, completely constrained, right? So whenever my movement is completely constrained, okay, so is completely restricted or constrained. That is called as homogeneous. This boundary condition are based on the displacement or the slopes. So these things, okay. So like movements. So if it is constrained, completely constrained, that is homogeneous. Let us say second example. Uh, if I have a simple bar, okay, and here I have another wall, okay. Now what I am doing, I am hitting this rod with some delta T temperature. So now this will try to elongate, right, in this direction because of this delta T. Now it will elongate until this reaches to this wall, okay. Let us say this is delta X until it reaches to this wall, and then after that it cannot expand or it cannot elongate, okay. So in this case, I am allowing some delta X, okay. I have not completely constrained it initially, right? So this can be called as non, because I am allowing some displacement, some elongation. So these are called as non-homogeneous boundary condition. Wherever I am constraining it completely, that is called as homogeneous. If I am not, I am allowing some displacement, elongation, deformation, then it is called as non-homogeneous. So that is based on the movement. Now, based on the forces, moments, and the loads and displacement.
Sir, actually, sir, I have one query.
Yes,
So what about that BCS movement, sir? Homogeneous BCS. What is the full form of BCS?
BC is like
Based
no,
on
no, no. That is boundary condition. BC is like boundary condition.
quantity?
Like
I didn't understand, sir.
BC is the boundary condition. Short form
Okay,
of
boundary
okay,
condition.
short. Yeah.
Okay, sir. Okay, understood.
Now, based on the loads and displacement. Okay, so now based on displacement,
Loads and
Sorry.
displacement. Okay.
Okay. Now I have first that is natural boundary conditions. Second, that is essential conditions. Okay. Now, whenever I have boundary conditions with respect to load or some moment, some torque, all the loads are some this kind of things. Okay, so these are called as natural boundary conditions. Whenever I have boundary conditions given with respect to displacement, or let us say slope, or deflection, expansion, some kind of these things. Okay, so deformation, these kind of things. Then these are called as essential boundary conditions. With respect to load or movement, it is called a natural boundary condition. With respect to displacement, this slope, deflection, expansion, this kind of things, they are called as essential boundary conditions. Any query in this? Any query?
No, sir.
Okay. Now we have the last thing. Generally, it is very favorite topic for all of the interviews whenever you are appearing for interviews like for the FE engineer. So this is symmetry boundary condition. Symmetric boundary conditions. Okay. And what are the needed things? I will list down first. If loads are symmetric, then material properties are symmetric, Then third, just a minute. Okay. So what conditions are there? If loads are symmetric, material properties are symmetric, geometry is also symmetric. Geometry is also symmetric. And the last thing, boundary conditions are also symmetric. Bases are also symmetric. Then we can apply symmetric symmetric boundary condition. Or we can apply the symmetric, not only boundary condition. We can apply symmetric. Okay. Now, why this is why to always look for the symmetry? Let us say if I have this plate, okay, and if I let us say this is 10 meter by 10 meter plate. We have only 2 minutes remaining. If I am able to finish this within that will be good. Otherwise, we have to rejoin it. Okay. Let us say We have some sigma here, and we have some sigma here. Right. Okay. Now, this is symmetric. And if I apply the symmetric boundary condition, I can take only this part. Okay. And if initially, let us say I had 10,000 elements. Now, if I consider only this much part, so with quarter symmetry, right? I am taking only quarter part, right? So I can have only 2500 elements. Now my elements are reduced, number of elements are reduced, right? So my analysis time will be reduced, right? And I can save time and efforts as well. So that's why whenever we have one symmetric boundary condition, we should apply that. Okay. So we can stop for this lecture and we will continue in detail for the symmetric boundary condition. We can revise that what all things or what type of symmetric boundary condition we can apply. And if you have any doubts, I will share the link with you again, and we can discuss on that. Okay. So please join for 2-3 minutes, and here we can stop. Okay.
Sure.
Yes, for the session we will be joining again for the doubts. Just because this Zoom meeting will be ending within few seconds. Okay. So I will send you the link
Sure.
and we can discuss it. Yeah.
What? So tomorrow is a lecture, sir?
Yes, yes.
Okay.
Oh no, tomorrow is holiday.
Tomorrow is holiday, na, sir? Okay, once lecture is started, sir, please share that link so we'll be able to join that.
Yes.